In this 8th podcast, we're going to look at the atomic structure and basically why elements stick together to form compounds. In the previous podcast, we saw that baking soda or sodium hydrogen carbonate is made up of several atoms, and they all stick together to produce that new compound for a reason. So that's what we're hoping to answer the question of during this podcast, is why they stick together. So first, the atomic structure. We need to look more deeply at what atoms are made of. They're the smallest piece of a given element, but they can be divided into smaller, more fundamental pieces. So let's have a very, very close look at an atom. So this arrow here is pointing at an atom, which you can't see because it's too small. If we zoomed in about 1 billion times, we might see the atom, and we might see something like this. So 1 billion times larger, we can see this sort of sphere, very sort of cloudy looking thing. Maybe if we peered deeply inside it, we'd see a tiny dot. Now the dot that you see on the screen here is actually drawn about 100 times too big. If I drew it smaller, you wouldn't even see that. That tiny dot in the center of the atom is the nucleus, and this sphere is really an electron cloud. Electrons moving very fast indeed, so we can't really discern the individual electrons, but they sort of fill in all the spaces and produce this relatively solid looking sphere. Now that doesn't tell us a huge amount about the structure of the atom. So what chemists and scientists like to do is they like to draw atoms in a slightly different way so they can visualize what's going on. For example, this is a pretty standard drawing of an atom, a chemist's drawing of an atom, and we can see the nucleus and the electrons, not drawn to scale and not really drawn in their actual positions. But this diagram tells us a lot more than the previous diagram. So what does it tell us? Now if we look at the key, red for protons, blue for neutrons and green for electrons, we can see that within the nucleus there are two different types of particle, protons and neutrons. Outside of the nucleus there's one type of particle, the electron. And the electrons seem to be positioned in different orbitals. And the orbitals correspond to how much energy the electrons have. The ones that are closer to the nucleus have less energy than the ones that are further from the nucleus. Now the reality is they aren't really in these fixed orbitals in terms of their position, not like planets around the sun. These orbitals, as I said, represent the amount of energy they have rather than their position. So the electrons can be anywhere within the confines of the atom, but they have a fixed amount of energy. The nucleus is tiny. This is not drawn to scale. The nucleus is tiny. It's about 100,000 times smaller than the actual atom itself. Very, very small. If you thought of maybe in terms of the correct scale, the world being an atom, our school building would be the nucleus. So the nucleus is very, very small. But it does contain almost all of the mass of the atom, because the electrons are really, really small and light compared to the other particles, about 1/2000th of the mass of the other particles. So in the nucleus we've got the protons and the neutrons. The protons have a positive electric charge, the electrons have an opposite negative electric charge, and the neutrons don't have any charge at all. The number of protons is very important. Now we can see that this has 6 protons. The number of protons really tells us what type of atom we've got here. And how the electrons are arranged is the key to why atoms stick to one another or don't stick to one another. This is one kind of atom, the kind of atom that has 6 protons. But there are kinds of atoms that have 1 proton, or 2 protons, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10, all the way up to around about 120. So far, scientists have identified 120 different elements, all with a different number of protons. That is the key to whether an element is different or not. Now, these different elements can be organized very nicely in something called the periodic table, which essentially is a grid this shape. Now, originally the elements were put into groups based on their chemical and physical properties. And this one here was group 1, where all the elements in this column here called group 1 would have similar properties. Group 2, likewise. Group 3, 4, 5, 6, 7 and 8, missing out this section in the center here. So vertically, these columns contain elements which would have similar properties. Now, since we've discovered all these subatomic particles, we can now see very clearly why elements in these columns have similar properties. This element has 1 proton. This element has 2 protons. This element has 3 protons, 4 protons, 5, 6, 7, 8, 9, 10, and so on. 11, 12, 13, 14, 15, 16, 17, and 18. So that's the proton number. Now, in an uncharged atom, an atom where the number of protons is equal to the number of electrons, we can see that this number is also the number of electrons that are in the atom. Now, if we go back to the previous diagram, we can see that electrons are arranged in a certain way. There are different orbitals, and the orbitals have electrons in them, but the first orbital can only have 2 electrons. The next orbital can have a maximum of 8 electrons. The next orbital, the third one, can also have a maximum of 8 electrons. So there's a pattern that has to be followed there. So if we look back at the periodic table, we can see that the first row of elements, the first row here, let's call this 1 as well, the first row here, both of these elements here would have electrons only in the first orbital. These elements here would also have electrons in the second orbital. This row here would also have electrons in the third orbital. We can go a step further and we can say that this element here, in fact this column of elements that I've just highlighted in yellow, would have each orbital full of electrons. 1 orbital, 2 orbitals, 3 orbitals. This element here, element 18, would have 18 protons. If it's uncharged, it's going to have 18 electrons. 2 in the first orbital, 8 in the next orbital, so 2 plus 8 is 10, and 8 in the next orbital. 2 plus 8 plus 8 is 18. Elements in the first column, however, would have only 1 electron in its orbital, or in any orbital. So element number 1 clearly has 1 proton, and it's going to have 1 electron in its first and only orbital. Element number 3 here has got 3 protons and 3 electrons, 2 in the first orbital and then 1 in the second orbital. Why can that electron not go into the first orbital? Because the first orbital can only have 2 electrons. This element here, element 11, has got 11 protons and 11 electrons, 2 in the first orbital, 8 in the next orbital, 2 plus 8 is 10, and then 1 electron in the third orbital. Let's look at one more column. This column here, group 7, this is element 9, and this one here would be element 17. Element 9 has 9 protons and 9 electrons. It will have 2 electrons in the first orbital, only 2 because that's full, and then 1, 2, 3, 4, 5, 6, 7 electrons in the second orbital. 2 plus 7 is 9. 7 electrons, meaning there is a space for an extra electron, or there's 1 space in the second orbital. Element 17 has 17 electrons, 2 in the first orbital, 8 in the next, that's 10, and 7 in the third orbital. 7 in the third orbital, where there's a maximum number of spaces for 8 electrons. So just recapping, we have the rows, which are known as the periods, and we have the columns, which are known as the groups, and the numbers that we see inside are the proton number, or the atomic number of the element. That tells us the number of protons and the number of electrons here. Each group contains elements that have similar properties. We will pause there and continue in podcast number 9.